So these lectures, there are going to be 3 on the QuickChik tool, are an introduction to so-called property-based testing in the Coq framework. And many of you, I think I remember a lot of hands went up when I asked how many Haskell users there were in the room. How many people have actually used QuickChek in Haskell? Almost everybody, okay. So that portion of the room, looked like maybe 2/3 or so, is very familiar already with very much of what I'm going to be saying. We're just translating it into the Coq context. Let's see, we'll have, so I'm going to talk for a minute about why you would want to do this. And then we're going to spend today on introducing one little bit of background, which is the type class mechanism in Coq. The idea of type classes is probably familiar to many of you from Haskell or other languages, but the way it's realized in Coq is a little bit different, and it's actually quite useful to lift the hood a little bit and look at exactly what happens. So we'll spend this morning on that. This afternoon we'll talk about the basics of QuickChik. And once again, I'll take a sort of Frankenstein approach, a build your own monster approach to it, and try to show how you build up the internals of QuickChek in a Coq context from scratch. Then on Wednesday morning, not I, but Leonidas Lampropoulos, the main developer of QuickChik, will give a lecture on kind of illustrating how to use QuickChik in a realistic context of testing properties of a small compiler. And then we will close with a kind of a transition lecture that will be Wednesday afternoon. Sorry. Tuesday morning will be Leo's lecture. Wednesday afternoon, I will give one last lecture on illustrating how to use testing in the deep spec context to specify and test a very, very small web server. Well, so small that it isn't actually a web server. It's a sending back bytes kind of server, but illustrating the essential properties of server applications such as web servers. So we'll see a complete story there of testing in that context, and then at the end of the week, Leonard will pick up that story with showing how to use the same specifications for proving in VST the properties of that server code. So that's the trajectory of this kind of integrative aspect of this set of lectures this week. So now back to QuickChik. So first of all, what is QuickChik? As the name might suggest, it is a Coq. Originally, it was literally a Coq transliteration of Haskell QuickChek into Coq. So since Coq has a type class mechanism and functional programming and all that, you could really take code from Haskell like QuickChek and just translate it over, even code that makes quite heavy use of the type class mechanism as QuickChek does. That's where we started. Then since then, for the past few years, we've been developing it in the Coq ecosystem. So how do you make a testing tool useful in the context of code where you're eventually going to verify most or all of it? And so we've been doing things like how do you automatically build generators for random data that satisfy inductively defined predicates. And you can look at our POPL paper this year for details on that. We won't be able to get quite that far, unfortunately, but basically beefing up the automation and the integration between the testing and proving aspects of QuickChik is what the project is all about now. So back to the basic question, why is this a useful thing to do? Why would we want testing in a proof assistant? And the simple answer is because almost always when you're trying to prove something using a proof assistant, the thing you're trying to prove is not true. So you would like a fast way of finding that out. one way of finding it out is to attempt to prove it, and a few weeks later you discover, this is why it's not true, and then you have to roll all the way back and redo the definitions, and or if you're Adam, just hit the button and replay your carefully designed automation. But in any case, a lot of work has gone into the process before you ever get to something that has a chance of being verifiable. So the idea with random testing in this context is to make it really fast and smooth to experiment with induction hypotheses, to experiment with changing definitions, and even with the somewhat complicated inductive invariants that one often ends up using to quickly generate counterexamples and see why it's not going to work. QuickChik started out as a kind of research system a few years ago. It became ultimately the topic of Leo's PhD dissertation, which is just finished, and it is now being picked up quite actively in the Coq community. So it's now the QuickChik implementation is part of the continuous integration of the Coq system, and so on. So it's really becoming part of the Coq ecosystem, we hope. As part of that, we have now a book on property-based testing in Coq, which is volume 4 of the Software Foundation series, and you are the first readers of that book, so you can find the first draft of it as the subdirectory QC of the DSSS 18 repo, and you'll find things to read, but especially a long sequence of quite carefully designed exercises to get you up to speed on the type class background and also QuickChik itself that I hope you will find entertaining. So let's dive right in. So suppose we define a function, let's call it remove, that takes a number and a list of numbers and removes that number from the list. We might write down a conjecture about that says once you remove x from L, x is not in the result. The keyword conjecture in Coq means basically the same as axiom. So it says I'm defining a property, but I'm not going to prove it. What could we do instead of proving it? We could check it. Okay, so the property is actually false. You probably all realize that already from looking at the definitions. But in case you didn't, let's find out why. So let's go to our Coq window, make it a little bigger. Uncomment this. I commented it out so that it doesn't run every time when we're processing the file. Okay, and it says, let's make this a little bigger. It says, no, your conjecture was wrong, and the counterexample is the number x and the list, the number that is the value for x, 1, and the list 1, 1. And the error that you all noticed the first time around is that the remove function only removes the first occurrence of a given number from the list. So an obvious mistake, and in this case, an easy counterexample. So in general, so this is the workflow of using QuickChik in Coq. You write down some definitions. You write down a property of those definitions, which is in the form of a conjecture. Here it was. The conjecture is a perfectly ordinary Coq assertion that has the special property that that QuickChik understands how to convert it into a Boolean test. And that is, it's a decidable property, and QuickChik understands how to decide it. The mechanism by which all of that conversion from this to a Boolean happens is a little bit of type class magic, which I will show you this afternoon. But it all happens pretty conveniently, and we see the counterexample. Okay, so that's the overview. That's where we're going. So property-based testing uses the following ingredients. So we start with an executable property plus a generator for random inputs of the inputs to that property. What are the inputs to the property? They're the universally quantified variables. We also need a little bit of infrastructure for printing out, for example, lists of numbers. And the thing that was a little bit hidden here, but is actually quite important in practice, is we need to be able to take a counterexample that has been found by random search and crunch it down to a small one that is easy for the user to understand. And that process is called shrinking. All right, so we're going to see all of that. But for the next little bit, for the rest of this lecture, we're going to look at the lowest level part of that, which is the type class mechanism. Then, as I said, this afternoon, we'll cover the QC chapter. Leo will cover the TIMP chapter. And then there are two more chapters that we won't cover in detail, but that you can read. The first is a chapter on using QuickChik in the context of larger developments with many files. And for that, we provide a command line interface with a few extra features. And then, so that interface is kind of parallel to the interface you just saw, which is invoked from within Coq. This one you invoke from the terminal. And then the final chapter in the book is a reference manual for QuickChik. So this new volume of Software Foundations is a complete introduction and reference to everything you need to know. All right. Dropped. Spell it correctly. So type classes. For those of you that haven't seen them before, the motivation for type classes is very simple. It is that we often have lots of different functions lying around with different types and different names and related functionality, but not functionality that is so similar that we would just abstract out a type and make it polymorphic. So type classes is for situations like where we want to print things, and we would have a show Boolean, show nat, et cetera, et cetera. So we want to have just one function show so that we don't have to remember the names of all of these things. But show is not a parametrically polymorphic function. It doesn't behave the same on Booleans and numbers. Rather, it does something related but different on those two types. Moreover, we want to have combinators for putting together show functions. So we could have show list and show pair and so on. And out of all of those pieces, we can manually construct printers and related things for structured types. But there's a lot of boilerplate and kind of annoyance and remembering the names of things that feel like you shouldn't have to. So the type class mechanism is for cleaning all of that up. Coq's type classes are based on Haskell type classes. However, the difference is that in Coq, the type class mechanism is not quite as special as it is in Haskell. So in Coq, there was already machinery in Coq to do most of the things that are needed for implementing type classes. So the developer of the Coq type class mechanism, Mathieu Sauzeux, added a few things, but mostly it's just a layer of syntax around kind of bundling features that were already there. That's good because it doesn't complicate Coq too much more. However, it has a downside that's worth understanding right from the start, which is that Coq's types are very much richer than Haskell's types, and therefore some of the things that the Haskell implementation of type classes is able to do for you, like detecting overlapping instances, are much more difficult to do in Coq, and the Coq type class mechanism will not do those things for you. So what that means is that it's easier to shoot yourself in the foot using Coq type classes than Haskell type classes. And heavy users of type classes in Coq actually shoot themselves in the foot many times a day. So the real skill with Haskell type classes is understanding what's going wrong when the type checker diverges and how to quickly get yourself unstuck. So in order to develop that expertise, that skill, it's really important to have a pretty clear understanding with Coq type classes of how things are working under the hood. That's what I'm going to try to show you in the next hour. For those of you that are not used to Haskell type classes, one caution is that there's a temptation to think about type classes in object-oriented terms if you're coming to it for the first time, and that is usually a mistake. So although the terminology looks a little bit similar, people talk about classes and subclasses and instances, you should really put all of your object-oriented intuitions on the side and accept this as something completely fresh. There are parallels and you can set up analogies, but it's kind of tricky. Okay, so let's go back to our show example. Here is our first type class. It's introduced by the word class, then we give it a name. Names of type classes by convention are usually capitalized, and we mention a variable A, a type variable A. And then we give what looks like a record syntax. And indeed, each type class can mention several operations that come with it. Here there's just one. So this type class has a show operation that takes an A to a string. So the way to read this is that show is a collection of types. And the types A that are in that collection are types for which we can define a show operation mapping an A to a string. Okay, so this show type class classifies types A with a show operation. And here, for example, is an instance of this type class demonstrating that bool is a show thing. So that bool has a show instance. So we give a name to the instance. We don't use this name very much because most of the time the type class mechanism is going to fill it in automatically, but occasionally it's useful to be able to name it. I think you can actually leave it out if you want, and you will see code that does it that way, but I prefer to put it in. And now here is the definition of the show operation for bool. It's a function for bool to string, a completely vanilla bool to string function. Okay, we can define show instances for other classes, like if we have a class, a type of primary numbers, we can have a show primary function. We can use pre-existing functions like string of nat to define instances. And now, okay, we have a show type class. We have a few instances. Now we should be able to use those instances to define other things. So here is a function called show1 that takes an element small a of a type big A where, and now here is the new